and good afternoon, Atreya. Today we are going to hear from Atreya Majumdar. So before talking about the alma mater of Atreya Majumdar, I want to comment something. That is, we all have a few of our seniors who actually have a large impact on our lives in both academic career and, as I said, life. So Atreya is one of them for me. So he completed his bachelor's in Presidency University. Then he moved to Groningen for top master's program in nanoscience. And now he is currently a PhD student at CNRS. So we will hear from Atreya. I will request everyone to please mute their audio and video, and we will accept questions after the talk. I request you to please raise your hands or type your questions in the chat. So over to Atreya.
Thank you so much, Ognivo. That was a rather overwhelming introduction. It was very nice. And so good evening to all of you who are from India or from Australia. Good morning to the people from United States, and good afternoon to my friends from Europe. So this is a fantastic opportunity where I can talk about my work with people who are literally all around the globe, and especially from a platform of Presidency, which is always very special, and it really brings back a lot of memories, although it has not been too long since I left. And so coming to my talk, I will be talking about some very disparate sounding things: rise of AI, climate change, and some electrical circuit elements. And basically the title of my talk is my outline, and using these I will try to present the background of the work I am doing as for my PhD project. So I will not go into too much details about the particulars of the work I am doing, but rather I would try to motivate why I am and my group are doing this work and why is it important. So, rise of AI. And this might really sound like something really fantastic and maybe something ominous, but that is something that we are getting from the popular culture. I would say the rise of AI is more along these lines. And here I just have two very simple pictures that I have taken from Facebook, my own Facebook account. And as you can see, when I go to these pictures, Facebook already knows who the people are. So there's this fantastic picture of our batch, and another very cherished memory of mine, which was when we played Copenhagen in my first year. And I can see some people from that play here today in the audience list. That is really fantastic. And Facebook very cleverly has already figured out who these people are. And in this section of the talk, I would try to show that rise of AI, what rise of AI actually means in today's world, and in which direction we are going. And at the same time, I would like to discuss this topic from a functional point of view. By functional point of view, I mean, we would just think about what input we are giving to Facebook or such systems, what outputs they're giving us, and how actually are they able to do this, like find the actual function that is doing this mapping. So in this case, the input is just these pictures that we are uploading. And what is Facebook giving us as an output is the identity of these particular individuals. And how is Facebook actually knowing this correct mapping? And that is by learning from all the uploaded pictures by the people. So whoever they can identify already have an account over these social media platforms, and Facebook has already knows who how this person looks. So this is how this kind of algorithms learn. And this is just one application, which is facial recognition. And there is even more from a more technological point of view application, which is very much upcoming. It's called autonomous vehicles or self-driving cars. And maybe a lot of you know that Tesla already has some kind of self-driving cars, although they are not totally autonomous. They require some assistance. But in some circumstances, like in a highway, they can really function as as an autonomous entity. And so how this functions is that this car has different kinds of sensors and cameras, and it gets information about its environment. And that is basically the input that we were talking about. And what the output gives is basically what the car should do under these situations. So maybe another car came very fast in the same lane, then it has to move very quickly to another lane. This kind of commands is basically the output in this kind of cases. And I must emphasize here that this is not only artificial intelligence, but also sensor technology as well as robotics that contribute towards this particular kind of cars. And how does it learn? Is it learns from actual drivers. So the data that is fed into this learning system is the same sensory inputs, but there's an actual driver sitting who is doing this kind of maneuvers in the car. And somehow from this, the system is learning to connect the information about the environment with what the driver should or should not do. Another application, which is much more within quotes creative and also interesting, is something called style transfer. So on the very left here, I have a picture of our very beloved Presidency at night, which is really beautiful. And on the middle, we have Van Gogh's Starry Night, about which I don't think there is much to say separately. And what this algorithm does is it takes the content from the first image, that is the Presidency image, and the style from the second image. And by style, I mean how the brush strokes are in the picture, how the texture is, all these kind of more microscopic things rather than the content. And it applies these styles, these very small textures to the content image, and we get something like this. And there is a website called Deep Art where any of us can go and upload pictures to do this. And I would really recommend you to go there and play around with this, because it gives really cool results. And as you can see, it really has copied the style of the Starry Night picture, where these kind of swirls are really present in the sky as well. And so again, input output learning. So in this case, the input is the two images that we are giving. One is the content, one is the style, and the output is another image which has the content of one and the style of another. And in this case, the learning actually happens in a very different way. And what it learns is something very general. So it learns what it means for an image to have a content and a style. So it really knows what, so if you give it an image, it can identify which are the style components and which are the content components, so that it can overlay one on top of the other to generate the final image. So this is another kind of more general form of learning. And if some of you were in Orichoda's talk, he was talking about these features that different layers of a neural network learn different aspects. Maybe some of the layers are learning how much this kind of curls are present, or maybe some are learning what kind of small strokes are present, and things like this. So it is actually a very important how we are defining this learning as well, what it is learning. And then I would like to talk about another class of artificial intelligence. So since till now we have seen like image recognition, as well as some kind of composite applications. Now, there's another very big domain, which is called natural language processing. And what it simply means is the system or the algorithm tries to learn how a language works. So basically, it learns a language like we learn English, French, or Bengali, whatever. And there is a very particular class of model which is called GPT-3, and it's a very recent algorithm that has been published. I think it got published in the end of June of this year, and it became available by August, beginning of August or July. And so here I would like to maybe do something very small. I will show two texts, and I would like you to guess in the chat which of them is generated by this model. So you can just write one or two in the chat. If you go through this snippets and maybe write in the chat one or two. Okay, so I think all of you, almost all of you are saying it's the second option. But I think Debojyoti is the only one who is correct, and it's both that has been generated by this model. Just I think sorry, there was some issue with the chat box. So I must say, so both of these were actually generated by this model, and I would like to say how it was able to do that. Like you need to prompt it in some way to generate something, right? So I was talking about this input and output. So the input in this case were this first few lines. So in the first one, this phrase, below is a screenplay for a film noir, hard-boiled detective story by Raymond Chandler about the boy wizard Harry Potter. And in the second article, the title and subtitle were given as an input. And the output was this whole paragraph that it churned out. And so when we're talking about images, it's easier to visualize that we are giving it, feeding it images from which it is learning. But in case of language, from what does it learn? So in case of GPT-3, it is actually the whole internet. All the text in the internet is what it is learning from. So you can imagine how much of data that is. And I would come into more details about that in a bit. But it really needs the whole internet to be able to learn some kind of language, some basic structures of a language, so to mimic how we think about it. And so basically this was the part where I wanted to show what AI is capable of and from what. We are just giving it a few sentences, and it is giving us whole paragraphs, a whole detailed paragraph about those sentences. And I think that is quite powerful. And even people are saying that this language processing, natural language processing is very close to being solved. So we can get perfect translations, perfect text summarization, and this kind of things. So I'm actually building up the whole conclusion in different parts of my talk. So in the first part, I wanted to describe what I meant by rise of AI and what it basically entails. And in this case, we see that it can do many tasks which human beings can also do, but maybe they can do it much better or much in a more efficient manner. But one aspect that we come now is why now? Like why specifically in the 21st century, in this first decade, first 2 decades, why is AI booming now? Because many of the algorithms were already there since 60s or 70s. And two big reasons behind that are that because of the rise of the internet and digitization of in various forms, lots of data is being available in the form of some kind of labeling. So we really know that what is what, and we have lots of images, we have lots of texts, we have lots of essays which are available on the internet in a digitized form that we can easily feed a computer. And at the same time, in terms of computational power, we have also come a long way. Now we have graphics processing units which can do many things much faster. And so what does this mean? If we have lots of data as well as lots of computational power, is that if you look at this figure here, what AI means in this stage is basically this blue curve, which is deep learning or the learning related to neural networks, which I will talk about in a bit. And that depends very much on the amount of data. And so the more data you feed into the system, the performance gets much and much better, which is which when compared to traditional machine learning, it's not the case where there is some sort of saturation. So this never-ending monotonic relationship is what is driving AI right now. Since more and more data is being generated, we are feeding it into this learning systems, and the performance is getting better and better. And another thing that actually comes along all of these is with these developments, many newer neural network algorithms are coming up, and that is even pushing this whole thing even further, that is by helping in the performance. So I'm talking about neural networks and deep learning. So let us see what it is actually. So I was talking about this input and output mapping, and there's this function which can be something very weird looking or complicated. But actually it is not that complicated. It looks more like this rather than that very funky machine. And you can see there are many connections between different components. There are the circles and the straight lines. And this is basically where the neural part comes from. It's from the neurons in the brain, which are connected in a very intricate fashion with each other. So what happens is that these inputs are fed as some real number to this system. So it can be maybe each of these units is a word of a sentence. It can be the pixel value of an image. It can be anything which can be converted in some form to some numbers. And there is some kind of mapping or some kind of combination between them in various layers, in various ways to get to the second layer. And then they are again recombined to get another layer. And finally, if we do this enough time and in a correct way, we should get the output that we want. And that is also represented by a set of numbers, which we then convert into some meaning, which is the output. And I will not go into too much details about what this means, but maybe I'll just look at a very small subsection where 3 of these nodes are connected to another one by these connections. And if the value of these 3 nodes was x1, x2, x3, the output was A, and this connection strengths was W1, W2, W3, then how to calculate A is basically we take a linear combination. So W1x1 plus W2x2 plus W3x3. So this connection basically say how strongly does the value of A depends on x1. So this is actually what lies at the heart of neural network, this kind of combination of inputs and weights, or how much weightage we are giving to each of these inputs. So maybe when we are trying to detect particular feature, particular digit in a handwriting setup, then it really wants to focus on a particular part of that digit rather than the whole picture. So in that case, the weightage of that part would be the most. And so what we want to remember from this part is, to be able to implement neural networks, we need to be able to multiply and add numbers. And to find the correct mapping from these inputs and outputs, there should be a correct set of these WIs. So we need to be able to change them so that they really give the correct mapping and they are just not randomly giving some results. So these are the two components that we need, and that would be important in later in this talk, that we need to take the linear combination, as well as we need to be able to update these parameters according to our will. So we're talking about these parameters and everything, which is defining the function. And I really like this quote from John von Neumann, that if we have a couple of parameters, we can maybe describe something. If there is one more parameter, it becomes much easier to describe that. So this numbers 4 and 5, actually the modern day machine learning engineers really took it up a notch, and they really went to 175 billion parameters, which is the number of parameters for the model that I showed you with the two text snippets called GPT-3. And this model had a predecessor which was called GPT-2, which was actually published not long back, just 1 year ago, and it had 116 times less number of parameters. So you can imagine the exponential number of growth of parameters that is occurring. And so having more number of parameters means is that a model is, or function has more degrees of freedom to move around. So say if we had a straight line passing through the origin, in that case there was only one parameter, so it always passed through the origin and only the slope could have changed. But if we now add also the intercept as a parameter, then now it can move much easily. So it can change its intercept, and it can really be any possible straight line. So that is the impact of having more number of parameters. And not only that, because if we have more number of parameters, it also needs much more data to train properly. Because we know, like if we had 2 data points, we can always fit a straight line through it. But if we had a more complicated function, like say a parabola, then 2 straight lines, we need much more data in that case. So so as I mentioned earlier, that for GPT-3, the training was done on basically the whole internet, which was kind of almost 45 terabytes. And it was actually more than that, because it also went through a catalog of books as well. So it was even more. And all of these are not, of course, not free. There's some consequences of it. And the most glaring of this consequence, I think, is on our climate. And to quantify this, actually, last year, they made some estimations about how much carbon dioxide in pounds is generated for just training one such model. And you can see in this right figure that just whereas average human life year, it's about 11,000 pounds of carbon dioxide equivalent. In case of transformer, which is a particular kind of model, also a language model, it is orders of magnitude larger. And I would like to point out where this one is. This one is somewhere around this one, I think, 230 million, whereas in this scale, it's 20, 40, 60 billions. So it's 0.2 billions. So you can imagine, with respect to that, GPT-3 has I think 1,000, yeah, 3 orders of magnitude more. So this number would also rise accordingly. Although there's no calculation done for this exact model yet, but the numbers should be around that, because it's using similar GPUs and other computational resources to do that. And these computational units have not become more environment friendly. So the trend in machine learning now is to add more parameters to the model, to add more data to the whole system, which basically needs much more training time, or doing it more in a more intensive fashion, and which essentially leaves a much bigger carbon footprint. And if AI is the future and we are going in this direction, then this can have very serious implications for our climate, if it is having such huge amount of carbon footprint as and so this is the part where I wanted to talk about the impact on climate. Like, this rise of AI we are seeing is not coming from free. There is some kind of cost we are having to pay in the form of some compromises in our climate. And so in the next part, we would see actually why is this so? Like, why is this so energy intensive? And from that point of view, I would like to talk about how computers compute, or like how the conventional computers which we are using right now to view this presentation is computing. And this architecture, how it does so, is called von Neumann architecture. And the main features of it is basically the memory unit, which stores all the values, all the informations, and the logic unit, which does this arithmetic or logic operations, are two separate entities. Like on the chip, they are physically separate. And in the context of neural network, we were talking about this parameters update as well as the multiply and add. So the parameter values are stored in the memory, and this multiplications, additions are happening in the logic unit. So when we are going through a neural network, the values of the weights or the parameters W1, W2 are being brought to the logic unit. There, they're being multiplied with x1, x2, x3, and then added. And then we are, by some algorithm, we are updating the values of this W1, W2, W3, and putting them back to this memory unit for being used in the later steps. So what is the energy cost of these different processes that are happening? So if we look at this table, the addition of the data, if we say it's 1 times, with respect to that, accessing the data, which means this bringing the stored values from the memory to the logic, it can be as high as 3,500. So you can see the bottleneck is actually not in doing this multiplication or addition, but it is in this shuttling of data from the memory to the logic, and from the logic to the memory. And this bottleneck is actually called von Neumann bottleneck, because it's energy efficiency bottleneck of von Neumann architecture. And this is basically the crux of this part, that the transfer of data is causing the most amount of energy expenditure. And if we can cut on that, that can really reduce the amount of energy that's being consumed in the training of neural networks. So basically what we do now is we take inspiration from biological organ that we are almost always using, and that is the brain, human brain. And just some facts and figures about the human brain, which are nevertheless very interesting. It has 86 billion neurons, and almost every of these neurons have more than 1,000 synaptic connections. So these are basically connection between two neurons, and can be viewed kind of as the parameters of our brain. So you see, it's already much more than orders of magnitude more than 175 billion parameters, which is the biggest model that is existing right now. So our small brain can really do a lot because of this connection, lots of connections. And it can do lots of different kinds of pattern recognition tasks. And the big point here is it does all of these just by using 20 watts of power, which is kind of equivalent to the power consumed by a light bulb. And that is really fascinating because it's doing so many things at the same time, yet consuming so little amount of power. And the reason behind this is basically how the computation occurs in our brain, as opposed to how it occurs in an actual conventional computer. So if we look inside the brain, there are these entities called neurons, which I have been referring to before. And there are these synapses, which are the connection between two neurons. So if we view this synapses as the memory unit, that is basically this connections is the connection strength between two nodes, which were these Ws, and this cell body, if it's the logic unit, because this is where all the processing happens, like inputs from different, these dendrites are these connections which are going into the cell body. So from other neurons, input is coming into this, and then there's some kind of operations being done here, and it goes on to the next neuron. So this cell body is basically where the logic part is happening. And the trick here is that this logic and memory are really located in the same, located very close to each other physically. And that means there is no loss of energy in shuttling the information between these two compartments. And essentially, this is the inspiration and the computing paradigm that comes from this kind of ideas is called neuromorphic computing. Neuromorphic means something which is similar to the nervous system, and computing is computing like how the nervous system does. And so this is the idea that in order to get away with the issue of consuming too much energy, we take inspiration from a biological system where the computation happens in a much more different way. And we must remember that the brain has actually evolved over a long time, and it really learned to optimize the energy consumption, because our body has a fixed intake of food and it has other needs. So it really had to optimize every aspect to get the most out of the energy budget that it had. So this can be a really interesting inspiration for computers, and not for all kinds of computers, maybe the computers with which we want to do some pattern recognition in those cases, because our brain is not too good at multiplying like 2 6-digit numbers. But if you give it a very, very blurry image of your beloved person, it can still recognize. So for those kind of more pattern recognition kind of tasks, it can be much more efficient. So we need something where the memory and logic are co-located. That would lead to this going away from this energy, the von Neumann bottleneck, which was consuming a lot of energy. But with conventional electronics that we have, there are very designated elements which account for the memory, like there are magnetic RAMs or magnetic elements, capacitors, which take part of in the memory thing. Whereas in logic, there are transistors, which through some kind of Boolean operations are doing this arithmetic. So what whatever electronics is available around us is not really enough to do this in-memory computing. So what to do now? And we need to also remember again, this kind of remember that all our ultimate goal is to be able to multiply and add numbers, as well as being able to update some of these numbers. And I will now deviate a bit and talk about something different, and it's related to symmetry. And I think today is a fantastic day to talk about symmetry, because today's date is so interesting. And this symmetry is actually related to some very basic electrical quantities. Like, so we have basically charge, voltage, current, and magnetic flux, by which we can describe electromagnetism. And if we look at this, the edges of this square, there is a capacitor connecting charge and voltage. There is resistor connecting voltage and current. There is inductor connecting current and flux. And the diagonals are connected just by the derivative relations. But why we don't have something similar between charge and flux? We only know about R, C, and L. And is there something else? And that is the fourth circuit element I want to talk about. And that is the missing piece of the puzzle that we were discussing a while ago. And the new electronics that can actually help in integrating memory and logic. This element is called memristor or memory resistor. And I will show in a while why it is called a memory resistor and not something else. So first, I would like you to focus on this equation, how it relates to the differential of the flux and the charge. So if we just divide it by infinitesimal time, so the left-hand side turns into voltage, whereas the right-hand side, this part, turns into current. So this is something very reminiscent of Ohm's law, right? V equals IR. So this M is actually a resistance, but there's a catch. It has a dependence on Q, the charge, and the charge is basically the integral of the current that has flowed through the system. And that has integration over a period of time means there is the history of the charge that has flowed inbuilt into this element. And that is why it is called memory resistor. It has the history of the electrical interactions within the system. And so how does this element actually look like? So we go back to our very basic kind of electrical characterization is the current voltage characteristics. So on the x-axis, there's voltage. That means we're applying some voltage and measuring the current of the system. Let's see how it behaves. So if we first increase the voltage, the current increases, usually very non-linearly to some value. And then when we decrease it, it does something like a hysteresis, and it follows a different path back to the origin. And so in this case, the value, how much it did this turn, depended on how far we went high up, because that means the current that has flowed through the system was much more. So it has a different resistance when it's coming down. And another situation is this, when we are really not going that far into the voltage, we are going much less. So less current has flowed through the system. So this value is now very different from what it used to be. And when it's coming back, it has a current path like this. And so putting all this together, what it means is that if we measured the current or the resistance state of the system at a particular voltage, we could have gotten different values of the resistance. So this is the key takeaway from this part, is that using this memory resistors, just by changing the memory or the history of how we are doing, how we are applying the voltage, we can change the resistance. And by changing the resistance, I mean changing the resistance at a fixed voltage value, which if you go through all the circuit elements, you know, diode, transistors, none of these have this property that you're getting different resistance value at when you're measuring at a particular voltage. So this is the uniqueness of memristor, and that gives us this ability to play with the resistance, and we really have control over how we are tuning the voltage, which is having its effect on the resistance. So this is one aspect. And secondly, another difference that it has from the hysteresis in magnetism is that at origin, it's kind of pinched. So when a zero voltage is applied, there is no dissipation. And not only that, it still remembers the resistance state it was in. And this property is called non-volatility. So say we have trained a neural network and we are not using it right now. We will use it maybe tomorrow. It does not consume energy in the time in between. It remembers the state it was programmed into, and then it goes back to zero, and then we are forgetting about it. Then we're coming back. When we're reading it at the same voltage, we are getting that particular resistance state back again. So that is the lack of volatility of this particular memory, as well as it's not consuming any energy to remember that value. So this ability to change the resistance to our need is something that prompts us to think about this resistance as maybe the parameters, because the parameters were something that we wanted to be able to tune by our own choice in a very easy manner. So this resistance can play the role of the parameters. But this is not all. We should be also able to do the add and multiply thing very easily. And for that, let us go back to our 11th or 12th standard, where we studied about Ohm's law and Kirchhoff's law. So with respect to one terminal, if we apply three voltages, V1, V2, and V3, there were three resistors like this. Then the current we would get finally is has some form like this. So this is very basic Kirchhoff's current law. And this has some similarity with what we saw earlier in a neural network. So if these three nodes had values x1, x2, x3, and they had weightages W1, W2, W3, then the final output would have been a linear combination of them. So we can harness this similarity between how a neural network is computing with the combination and Ohm's law and Kirchhoff's law to put them all together. And that is actually called a crossbar array, how they are put together. So here, there are basically two series of electrodes, which are this yellow kind of bars, which are crisscrossed on top of each other. And at the intersection of each of them, there are these green cells, which are the memristors that I was talking about. And if we are applying these voltages, then depending upon the conductance state of each of these memristors, we can get different values of the current. And this current is basically the output of the network, and we can visualize it as the output of a neural network, because these voltages are getting multiplied with these weights, and that is getting summed up by just again Kirchhoff's law, and we're getting this final current J. So that was one aspect. Another aspect was to be able to update these parameters, that is modify the conductances. And because we have memristors over here, we can also do that by applying some special voltages to these components, which can change the individual resistance states. So say if we wanted to change the value of this one, we would have applied some voltage between this terminal and this terminal here that would address this particular memristor. So this is the idea behind actually having an on-chip neural network. So as of now, we are running all of these neural network or deep learning simulation on a conventional computer, which has this von Neumann bottleneck, and that was the cause behind the consumption of so much energy. But if we can directly now do these computations on the chip, where the memory and the logic are integrated in this manner, then we can get improvement in the energy efficiency. So this was the part about the fourth circuit element that I wanted to talk about, and how it can be a very interesting candidate in solving the issue of the carbon print of conventional neural network architectures. And so how it actually solves this problem is this integration of memory and logic in one entity, and these memristors are acting as these tunable parameters. So this is kind of the overview of the field that I am working on right now, where we want to do electronics with this kind of memristors to implement neural networks on the chip, which is much more friendly to the environment. And herein comes my research. So I will try to describe the problem. So when we are using a conventional computer, we are either using a 64-bit or a 32-bit memory. So everything is very precise to like a lot of places after the decimal. But unfortunately, when we are using devices, things are not so smooth. So when we are using devices, there are nonlinearity, device-to-device variability, intra-device variability present. And what this means is that, so we want to change the resistance value or update the parameters value in some fashion. And we want it to do in a very controllable way. Say if you want to change the parameter value by 2 times, then we would apply something very specific to that. But that is not so easy to do when we are actually doing it with devices. As an example of what I am saying, I have the plots of the resistance evolution for 2 such memristors that I have worked with. And on the x-axis here is a pulse number. So I was talking about how we are playing with the voltage to change the resistance. So here this pulse is actually some pulses of voltage. So the pulse number is the number of voltage pulses we have applied to our memristors to change the resistance state. And as you can see, there, first of all, it's non-linear. It's not a linear relation between R and T. There is device-to-device variability, which is very prominent. As you can see that the red and blue are 2 devices, and they are quite different from each other. And as well as there is intra-device variability, that is a lot of noise even within one particular device. So how will we reconcile this with actual neural networks where everything is very precise? We really need a 32-bit or a 64-bit precision for all the values too. So here is where we look into different kinds of architecture or different type of neural network. So in a normal neural network, which I'm calling vanilla neural network, and this vanilla means normal in the lingo of machine learning or artificial intelligence. And in these cases, the value of these connections or these parameters, as well as the outputs, they can be any real number. So they can be as small as possible, as small as you can imagine, basically, theoretically. And doing that exactly in a computer is impossible, because we really can go up to a finite amount of precision. So, but nevertheless, with the precision we have, it's usually enough. But when we are really using these devices which have a lot of noise intrinsic to them, it's not very helpful. So we look at another class of neural networks, which are called binarized neural networks. And in a sense, it's much simpler than normal neural networks because the values of these parameters and the nodes are either +1 or -1. So you can imagine that even there is some fluctuation in some value of the connection, it will remain within +1. And only when it is very really in the borderline will it go over to the other side. And that is that does not have a huge effect on the performance. And so this kind of binarization, in a sense, improves the robustness of the neural network. So this is the research goal that we are pursuing towards, to use these binarized neural networks. And it has been shown that these binarized neural networks indeed can actually perform as good as the already existing neural networks. Although there is some compression of information, because of course we were going from some infinite value in an infinite range to just 2 value. So of course there is some compression of information, but that can be made up by increasing the size of the network. So we were using more number of nodes, more number of parameters to get rid of that. But on the other hand, what we are gaining is this robustness to this device imperfections like nonlinearity and variability. And we are using the Memristors as some component that is integrating the memory and logic, which is in turn reducing all the overhead of this power consumption. And another approach is actually to use this kind of variabilities. So the neural networks I was talking about till now really was a deterministic network, but there are also other approaches to learning which are more probabilistic. So there are ideas to actually use these devices as a random variable, where the different features of this random variable are changing with more pulses. So this is another idea we are going towards, is how we can actually use this noise to do some computation. So this is kind of the whole story, that how we are seeing this very rapid increase in the usage of artificial intelligence, and that is causing some considerable amount of impact on the environment. We can do away with that by going towards some different kind of computational architecture where memory and logic are integrated. And with using that architecture, we use some different neural network algorithms to do the same tasks, so that we can get the same benefits that artificial intelligence is giving us, but without the harmful effects of it. So that was my talk. Thank you so much for listening.
Thank you, Atreya. It was a wonderful talk. We already have a lot of questions lined up. I'll read them for you.
Okay, that's fantastic.
So first, Doipayon asks, how does AI self-correct?
Okay. So if I understand the question correctly, maybe I'll go here. So Doipayon, the approach how a neural network learns is actually from self-correcting. So I'm just answering your question with your question. So how it basically begins is that these connections are totally random. So they have the input and output are really disconnected. So it starts from such a configuration. Then you give it an input, and you are having the output with you. So you're calculating, you're going through the network, and you're seeing what the network is predicting, and you're comparing the two, the actual output as well as what the network is giving you. And now you're looking at this difference, and you're changing the different parameters to minimize this difference. And this is not very different from the chi-square minimization that the curve fitting algorithms use basically. And so you can say that training of a neural network is some kind of a very glorified chi-square minimization. So it is the self-correction that lies at the heart of training neural networks. So I think that's my answer. If it's okay. Okay, good. Yes,
Okay.
happy with the answer.
So there are a lot of questions in the chat box as well as there are a lot of hands raised. So
Mm-hmm.
I'll go one by one, right? So Pritam Manna asks, in the graph where the performance and amount of data were plotted, why is it that old machine learning gives a better performance than deep learning at low data?
Okay, so let me go here. You mean this regime? Okay, yeah, I think that's a very good question. So, what is in the name of deep learning is this word of depth. And what depth means is this huge number of parameters that we are allowing it to have that it can tune to actually represent the function. So when we are having a huge number of parameters and we are giving it very little amount of data, it actually performs terribly bad. And there is actually a term for this, it's called underfitting. So you can imagine from a curve fitting perspective why that would be the case. So it's basically we have a parabola and we have 2 points or something you can imagine in that way. So it will really perform poorly in that case. But since there are so many degrees of freedom, when you are giving it more and more data, it is able to tune them much further and like tweak them really well so that the performance gets up after a certain point. But for small amount of data, because it is made in such a way so that it really needs the data to grow, it performs worse than other kinds of machine learning techniques. And I think I would say something more in this regard is that there are many instances in real life where there are a lot, because of practical reasons, not a lot of data is available. In those cases, this old machine learning models are still being used extensively. So I think Recherche, Ghosh, one of my batchmates, is here, and he has been using this kind of machine learning for his master thesis quite a lot, because the data they have is from physics, some physics experiment or something, and it's not huge. It's big, but it's not huge. So in those kind of context, this the conventional machine learning tools outperform. Yeah, that's the answer.
Okay, so next there are two questions from the chat which are similar. Mirade and Onik Parvi, both of them ask that in the neural network, why the output always have to be linear?
It is actually not at all linear. I just wanted to emphasize that how this linear combination happens. Actually, after we calculate this A, it goes through another function, which is called the activation function. And that really makes it nonlinear. And also, I should emphasize here very well that this nonlinearity is absolutely necessary for any kind of relevant task that we want to do, because linear really does not get us too far. And I think I simplified this part to just focus on this multiplication and adding. So that's why it appeared to be linear, but actually it is not. And I did not focus on that specifically because this nonlinearity that we are applying is the same for all the nodes. So all the A's that we are getting here are going through the same function. So that really does not cause any problem in terms of computational efficacy.
Okay, I think I shall first go to the raised hands and then come back to the chat box. So over to Ognivoda.
Hello, Atreya. Nice talk. I just have one small basic question regarding Memristors. So the first part to that question is, so what is the physical motivation behind trying to find a fundamental circuit element that connects the magnetic flux with the charge? So is it in anything more than just saying, okay, so you have three other elements, so you should have a fourth one as well? And the second part to the question is, has it been tried experimentally and seen that there's something called the memristor?
Thank you, Mimoda, for the compliment and the nice questions. So first of all, how the whole story of Memristors started is from symmetry arguments. So what I presented here is kind of very simplified version of what the person who first thought about this thought. So it's really from symmetry considerations that the very initial ideas of Memristor came about to be. And the second question, I think that's very relevant in this case. And I skipped a slide, and this gives me the opportunity to show it again, which was this one. So this is actually the current voltage characteristics of an actual memristor, which is hafnium oxide. And you can see this hysteresis very clearly. And this is actually the absolute value of the current. That's why for negative voltage, it's positive.
Oh, okay. Okay. So was this, so how was this made? So.
Oh yeah, that's I think that was a question I was expecting, and I have backup slides for it. So yeah, I'll. So memristor is not one particular thing per se. It can be very different kinds of materials. So it can be there. Very broadly, there are three classes which show this property. One is phase change material, where the phase of the material is kind of encoding the resistance state, because when it's say in solid, there is much more order in the whole system, and the wave function can really localize to a very large distance, and that means a low resistance state, that is the electron can be anywhere. Whereas if there is more disorder in the system, it can be the wave function has like some kind of localization, and that prevents electron from going far, and that's a high resistance state. There is a spintronic based approach where there are two ferromagnets whose relative alignment determines what resistance it will be. And the kind of memristors we were using is something called filamentary resistors, where in the high resistance state, so there is basically two electrodes between insulator, and this insulator is hafnium oxide, which I showed before. Hafnium oxide intrinsically is an insulator, so it's in a very high resistance state, and it can happen that some conducting filaments, like highly conducting filaments, can actually form between these two electrodes because of the motion of oxygen and forming oxygen vacancies that can lead to this low resistance state. So basically this is the idea, that you need to have some kind of underlying physical process which is causing this change of electrical states, and that is how memristors work basically.
Okay, thanks.
Yeah.
Okay, over to Olomkarta.
Am I audible?
Yeah.
Thanks, Atreya. It was a really wonderful talk. I'm really impressed by the simplicity and also the clarity with which you explained the stuff. So I just have a couple of questions. The first one is basically a query. So you were talking about controlling each of the memristors. So is it because you wanted to control the biases for each of the neurons? So you want to have tunable bias for them? Or is that the reason why you want to control each of the memristors individually?
Yes, so these memristors actually represent the weights and biases that are associated with a neural network. And in the training phase, what we are doing is using the gradient descent algorithm, we are calculating the updates for these weights and biases, right? And this is precisely the reason why we want to update it to actually train a neural network. If that answers.
Yeah, sure. And the final question is, how do you implement really the back propagation in these circuits? And is it quite versatile in terms of what cost function you choose or what activation functions you implement for each of the neurons?
That's a very interesting and difficult question, to be honest. So actually, what I showed here is the inference phase of the network, where it's given an input, it's calculating the output. more tricky thing to do is actually what you described, is the backpropagation algorithm, where we really need to calculate the updates and change the conductances individually. And just using this, it is not possible to be done. There has to be some additional transistor components which calculates these derivatives and everything so that we can do this. But the approach of binarized neural network that we are taking has a much simpler solution to this issue, and that can do this in a much more efficient way than just a conventional neural network. So, did you have another question?
Yeah, so is it also versatile in, as far as this setup is concerned, is it versatile in terms of its cost function you choose or the activation function you choose for each of these memristors?
I think not, because this is a strategy of having the neural network on devices or using devices. So if the cost function or the activations were already chosen to be implemented in a normal computer, I would say it will be similar as here, like a rectified linear unit would be better than a sigmoid for the neurons in the intermediate layers, and similar. Like, so in those cases, I won't say there would be any difference with how different. So the difference that it has in computer normal neural networks in computers will be the same as here.
And how do you implement finally this nonlinear activations in these circuits?
Again, that is not very quite inbuilt in this this very normal neural networks. But when we are going to binarize neural networks, since the final value is either +1 or -1, we do this kind of calculation, and then we just take the sign. So in that case, the activation function is very simple. It's just a sign function, so it's easy to do.
Okay. Thanks a lot.
Yeah.
Okay, so as we have an interaction session coming up next, so I'll please request you to keep your questions brief and maybe ask one question and return back to the second question, and we will return back to the second question if time permits. So over to Kaustubh.
Hi Atreya, thanks for the absolutely wonderful talk. I loved it.
Thank you.
So my question is, when, as you said, that binarized neural networks can perform equally well as to more continuous distribution of weights, but whenever you're converting a more continuous distribution of different weights into a binarized structure of neural network, that would mean it would need, I don't know, orders of magnitude more connections and weights and a completely larger reformatting of the entire structure, right?
Yes, you're definitely correct that, see, of course, we are really compressing some parts into just the sign of their values. So there must be some loss, we must compensate. So what is usually done is the number of hidden neurons, which is basically, let me go to a good image. Yeah. So the number of neurons in this intermediate hidden layer, that is made 3 times as large as one you would use for a normal neural network. And it is seen that if we make this 3 times large, then it can get to comparable accuracy. So it is not orders of magnitude, but it's also not small. It's 3 times. And I think here in this context, there might be a follow-up question. So I might try to answer it already, is that we are using devices. So if we are already using 3 times more device, it's not very ideal. So the thing there is that we are using this memristors, and this memristors can be really of the order of nanometers, because the processes that are happening there are very nanoscopic. So the size issue is not that much of a problem here. So we can do a BNN with 3 times or 4 times more number of nodes with and to get the same accuracy. Yes.
Okay, thank you.
Yeah.
Okay, over to Shashwata.
Hi, Atreya, can you hear me?
Yeah, sure.
Yeah, thanks for the really nice talk. It was really interesting. So my question is, so coming from, let's say, a person's perspective who just wants to use neural networks. So the things are interesting in themselves, but I just want to use it as in my data analysis or something. So like, which kind of problems would you say are the neural networks or different kinds maybe are more suited, and which kind of problems are less suited? So how should one approach it if one isn't like, okay, I have any problem, I just throw some different kinds of neural networks and see what happens? How should one approach this topic? If you can comment on that maybe a bit.
Mm-hmm. So the first thing I would emphasize here is neural network is not something magical. It's just a function, and like the mathematical basis behind this neural network stuff is something called the universal function approximation theorem. And it says that neural network can approximate any function with a certain degree of accuracy. So if you're doing some problem which you can formulate in such a manner where there is input and there is an output and it's mapped by some function, then in principle it should be able to be solved by a neural network. But as I try to say in my talk, that data is a very, very, very important aspect. And if you have less amount of data, this neural network, deep learning might just give you very poor results. So if you're working on a task where you can really define some inputs, some outputs, and you have a huge set of data, there you can I think you can use very confidently neural networks or some different kinds of it. And what kinds actually also depends on how you do the problem. Like, we can use a convolutional neural network or a fully connected neural network for image recognition or similar, or this kind of thing. So that is I think that's some other question. That's not your one. So yeah, data and problem formulation. These are, I think, two aspects that you should think about.
Yeah. Okay, thanks a lot.
Okay, so Arithro.
Hi, am I audible?
Yeah.
Yeah.
Yeah, okay. Thank you, Atreya, for the wonderful talk. So I have a similar question like Shashwata. Are any of the popular neural networks like CNN or ANN relevant for your work, or did you use any of those neural networks?
Yeah. So all the statements that I made that it shows state-of-the-art performance is actually using a fully connected as well as a convolutional neural network, and it has been shown that both of them work very well. But when we are using recurrent neural networks, it is not so good with binarized neural network, because as we are saying it, we were compressing data to just the sign, and that is really a very strong kind of compression. Some kinds of processes, some kind of networks which really rely on very small differences might be not very suitable for this kind of approach. So in the literature, it's not very well shown that recurrent neural networks or or LSTM or this kind of sequence model do very well with respect to binarized neural networks. It's mostly fully connected or convolutional nets which are shown to be more more compatible with binarized networks.
Thank you.
Yeah.
Okay, so we have two more questions in the chat box. So Debajyoti asks, in my experience, binarization or batch normalization has always come with loss of fidelity. In tasks such as data generation, could you tell me which tasks benefits from this, perhaps classification?
So first of all, I would say like data generation is, to my knowledge, an unsupervised class of problem. So binarized networks, to my knowledge, has not been applied to such cases. So it's mostly classification, like you said, that it has been tested against, which is a supervised technique. So I'm not very confident about how it would perform in those cases, because yeah, I would also imagine like you that it can have real serious consequences where there's a very nonlinear kind of issue with the values of all the parameters. Yeah, that maybe partially answers your question.
Okay, so there is another question by Sudipto. When you are converging uh, from infinite range to only two value -1 +1, as you have mentioned, we need a massive network, but then it will increase the computing time too. How much is the effect and how to reduce it?
So there are actually two ways to answer this. Maybe I will first try to say from like binarized neural networks on normal computers. So how conventionally we do this kind of networks is using GPUs in normal computers. We train this using GPUs, and in those cases, the network size is sometimes not that affecting the computation, because if we get the ability to parallelize very well, then this issue with computing time kind of gets reduced quite a lot. So say we are using just 300 hidden neurons, it is taking some time. It will take almost a similar time if you are using, say, 1 order of magnitude more number of nodes. So that is on a normal computer on a GPU, where we usually do this kind of computation. And another aspect is when we are doing it in using actual memristors and this kind of things. I think there is a strategy of parallelizing, as you can see from the figure that is on display in crossbar array. You can actually read off the currents I1, I2, I3, Ij at the same time. So when you have this sort of parallelization, I think the effect of network size gets reduced. But of course, like if you're increasing it by 2 orders of magnitude or something, it will after some point affect the time indeed. But from vanilla networks to BNNs, the transition is not that high, because as I mentioned, we really just need 3 times more nodes to get the similar performance. So yeah, this is the effect, and we really don't need to reduce it.
Okay, so this is the last question I'm going to take from Devajyoti. Are Memristors still in the development stage, or do we already have some benchmarks in terms of performance when compared to modern day GPUs? So I think he has already answered this question. But again,
maybe I will answer in short that I think it's very much in the development stage, and even today, different types of memristors are being discovered or designed, and various kinds of ways are being tried how we can use them for neural networks. So it's really very, I think, quite early and exciting times for people who are working in this sort of things. And yeah, even today, I think it has not reached benchmark of all kinds of everything that we have done in GPUs. Yeah.
Okay. So thank you, Atreya. If there are no more questions, so I actually have a very short question, or rather comment, where you showed the IV curve of the memristors. Can you show that slide once?
Yes, sure. You mean?
Yeah. This
cartoon one. Or yeah.
Okay, the cartoon. Okay. So this type of hysteresis actually allows you to get 2 values of current for a particular value of voltage, right? So
it can be more than 2, like
yeah, more than 2. I mean multiple values of current. So so that is how hysteresis is helping us in this regard. So I have encountered this type of IV curves in Josephson junctions, like superconducting Josephson junctions. So, I mean, can they be used as a substitute of these memristors? Because if we look into the IV curve of Josephson junctions connected to a current bias, then we get something like this. The IV curve looks similar.
So in that case also, is it a pinched hysteresis loop? Is it like at 0 voltage there is 0 current, or 0 current 0 voltage? Or
yeah, actually there is a cutoff. For example, here you have showed the dotted line. So up to that there is the supercurrent stage, so there is no voltage. I mean no current, although there is I'm sorry, actually in that curve there was the voltage plotted in the y-axis and current in the x-axis. So anyway, so in that case there was no current or no voltage drop up to a particular level, and it was considered as supercurrent because there is almost no resistance flow. And after that actually the voltage started to develop, and we get a hysteresis when we get back to the return journey, for example. And there we actually encountered, for example, in this stage below the supercurrent, there are two values, one for the forward journey and one for the backward journey. So that actually also had a significance in developing these kinds of computers back in 1980s, 90s. So maybe they can form a significance here.
Yeah, this is something I don't know anything about, but it sounds really, I think, similar to what this kind of memristors are. And there is no very hard and fast rule as to what can be a memristors, because as I showed a bit before earlier, that it can really be very different kinds of systems which are acting the role of memristors. So yeah, maybe in some kind of a thresholding sense, it can be a memristor as well. Yeah. I will look into this. Very interesting.
Okay. Thank you, Atreya. So I think I also have a question in the chat box, but we will get back to that question in the interaction session. But first, I'll request you to